So this is example 5.3.2 from the book, and this is pretty similar to what we were doing just a few minutes ago, or in the previous example. Basically it says, given the static friction coefficient mu sub s, how far out on a disk can a bug of mass m crawl before it comes off, right? And so the disk is spinning this way. Notice it's walking out the x-axis here. And it's traveling at velocity v prime, so it's traveling at a constant velocity. And the distance it is from the center we call x prime. And so I know there's a normal force, and a weight pushing in, but for the interest of the answer to the problem, we're really interested in how far it's going to, how far it can go before the forces on it cause it to slide off the disk. And so we can say, well, look, in the plane of the disk, the sum of the forces equal the mass times the acceleration. Again, this is in the inertial frame, right? And so the sum of the forces in the inertial frame is just the physical forces that are acting on the bug. And the acceleration is this complicated thing, which when we transform into the rotating frame looks like this. We've done this a bunch of times. This is the acceleration in the rotating frame. Again, same physical forces, right? Both of these are just going to be friction, basically. There's no other forces holding the bug on. But then all of these other forces from the rotating frame, and so this is the acceleration in the rotating frame. Well, if the bug's moving at a constant velocity, then this term is 0. And then the next term is the transverse acceleration. This is omega dot cross r prime. And once again, as long as it's rotating at a constant velocity, this guy is 0. And so we're really just left with the sum of the forces equal these two guys. In other words, when the magnitude of these guys exceeds the maximum magnitude of the friction force, the bug comes off. And so let me erase the board and we'll get to that. So what we're left with is the sum of the forces equals the mass times the acceleration. These are the only two terms left. It's omega cross v prime and omega cross r prime. V prime is just the speed that the bug's crawling with up the spoke, or along the disk. This is just similar to example 5.3.2. So it's going up walking along the disk, V prime up the x prime axis, and so this term just becomes 2m omega omega v prime times j hat prime, because if I point my hand towards the camera, that's the omega direction, and then I curl my fingers towards the v, I get that way, and that's what gives me a j prime. And then this term is omega cross r prime. R prime is just is distance from the origin, and that's just along the x-axis, so it's just x prime I hat. If I do omega cross x prime I hat, I get a j hat direction, but then I do omega cross that, and so that gets me a negative I hat direction back towards the center of the circle, which is the direction we expect for the centripetal acceleration anyway. And so then I can say, look, the magnitude of the maximum friction force has to equal the magnitude of the mass times the acceleration. The direction of these two guys is different. So if I draw the bug here, if I do a little free body diagram for the bug here, he's got an acceleration this way, right? He's got m times 2 omega v prime in this direction, and that's mass times the acceleration, and he's also got a centripetal acceleration, which is m omega squared x prime. And so the magnitude of those two is the diagonal of the box made by those, right? And that's what the force has to be. Since the bug is being accelerated this way and this way, the net force on it has to be this way, and so the maximum value of that has to be this. And so that says that m times mu sub s, the maximum friction force is mu sub s mg, right? And that's got to equal to the magnitude of this, which is, I can pull the m out, and I can say it's m times 2 omega v prime squared plus omega squared x prime squared to the 1/2. Right, and so if I wanted to solve for the for x prime, I could just solve for x prime. I'll do that on the next sheet. So let me just say a couple of things about this before we get done. As the bug crawls outward, right, first of all, we know that the centripetal acceleration is increasing because a sub c, just for a rotating bug, is omega squared r, right? And so as it goes out, it's going faster, and its r is bigger. Sorry, the omega is staying the same, but its x prime is increasing. So we know it's got a greater centripetal acceleration the farther out it goes, and so that's what tells us that there's an acceleration this way. And notice also as it walks out, it's walking into a velocity that's increasing in this direction. As you get farther from the center, your velocity this way is increasing because this part of the farther out you go, the faster you're going this way. And so the bug has to be accelerated in this direction and in this direction. And so the net force has to be the combination of those two, which is this way. All right. So the final piece of this is just solving for x prime, right? We got the sum of the forces, which was just the friction force, at least in the horizontal direction, is equal to this, because we have one acceleration going this way and one acceleration going this way, so the net force on the left-hand side has to be in this direction. That's what we did on the last slide. And so now I just I cancel the m's, I factor out an m, I cancel the m's, I square both sides, and that gives me this term, right? And then I move this guy over to the other side. I'm trying to solve for x prime, so I bring this term to the other side, bring this guy over here if you want, and I end up with this. I have to take the square root to get this back to where I can take x prime, and then I solve for, I divide out by omega squared. And so this is how far the bug can crawl before the friction force can no longer hold him on the wheel.